Hello, anyone who's bothering to watch this video. I'm making this video to motivate our study of measure theory, why measure theory is necessary. And I do that by showing that non-measurable sets exist. If we could extend the notion of measure to all subsets of R, that'd be great, but we can't. And it's actually a fairly easy proof that you don't really need too much background in measure theory to follow. And I think it motivates the whole study of measure theory. So first, maybe you're wondering why we bother studying measure, what we gain from measure theory. Well, we do get, uh, let's see, an extension of the notion of length or volume to more abstract sets. So we can talk about the length of an interval quite easily, but what about the length of the rational numbers inside some interval, or irrational numbers, or some more abstract set? So that's what we gain from measure theory. And as a consequence of extending this notion of measure, we also get a lot of nice forms of convergence. We can start talking about, instead of convergence at every single point, whether it be convergence of functions or what have you, we can talk about convergence almost everywhere. So convergence except on a set of measure zero, which really broadens our notion of convergence and gives us really powerful theorems like monotone convergence theorem and Lebesgue-dominated convergence theorem, which are really the strengths of the Lebesgue integral. That's why we bother developing this measure theory in the first place for, most of us. So there's really a pot of gold at the end of the rainbow. It's really worth the effort. So to motivate this extension of measure to more abstract sets, we should first show that it's necessary. That it's, well, not necessary, but it's not as simple as it looks. Why do we need measure theory? Because it's kind of complicated extending this notion of measure. There are, it turns out, sets that we can measure and sets we can't measure, non-measurable sets. So I think a good motivation for studying measure theory is the fact that these non-measurable sets exist. So I will be giving such a proof. This proof comes from this really cool book I found on a trip. Comes from this book, The Axiom of Choice by Thomas Jeck. It's a book, it's fairly thin, devoted just completely to the axiom of choice. So that's an interesting topic by itself, and really implies the existence of non-measurable sets. There's a couple of famous examples we'll talk about briefly here. But if you haven't checked out that, if you've never heard of that book, check it out. It's pretty cool. All right. So let's begin our proof that non-measurable sets exist. So before we begin, a little introduction. As I said earlier, our measure theory is going to be an attempt to extend the idea of length or volume of a set or an interval to more abstract sets and even more abstract spaces. When we're talking about measure theory or measure of sets, we can talk about measure of real sets, of sets of real numbers, and we can talk about sets on abstract metric spaces, things like that. So really get a very broad idea of what measure theory is. And it gives us a lot of great tools. For example, we're used to integrating on intervals. What if I wanted to integrate a function on the rational numbers between 0 and 1? How would I deal with that? That'd be very difficult or impossible to deal with using the Riemann integral, but using the Lebesgue integral, it's fairly straightforward. So these, again, are some of the advantages of extending this notion of measure to more abstract sets. We get convergence almost everywhere, convergence in measure. And then from these new notions of convergence, we get these powerful integration techniques: monotone convergence theorem, Lebesgue-dominated convergence theorem. However, we do run into some problems in this extension. If we try and extend our idea of measure to all subsets of our space, we run into some problems. So a famous example is the BanachTarski Paradox. If you accept the axiom of choice, the BanachTarski Paradox follows. It's pretty interesting. You can show that if you start with a sphere, you can decompose that sphere into a finite number of subsets and rearrange those subsets to get two identical copies of your original sphere. So it goes against our geometric intuition, because if you break up a sphere into pieces and rebuild it, you would expect to only be able to get, you know, your same sphere back. But using sets that end up being non-measurable, we can show that actually, you know, we can get two identical copies. So it implies this notion of size of set doesn't really transfer to all subsets of our space. It implies the existence of non-measurable sets. I'm not great at this kind of abstract or, you know, rigorous geometry, so I have looked at the BanachTarski paradox a little bit, but I prefer this proof of non-measurable sets that's due to Vitali. It's just purely analytical, not much geometry involved. So I'm gonna use that method. So before we show these non-measurable sets exist, I haven't really defined a measure, but if we think of it as an extension of length of an interval, we see some properties that we would like this extension to have. Okay, so I'm going to refer to this extension as a measure, even though we haven't really defined a measure properly yet. What kind of properties would we want a measure to have? First, it should be a positive set function. Okay, so let's try and construct a measure on the power set of R. Let's confine ourselves to R, and let's try and extend this notion of measure to all subsets of R. Okay, we're going to end up showing that that's not possible, but let's assume for a second it is. So we would like our measure to be a positive set function from the power set on R to the positive real line, extended real line. So we're allowing sets to have measure of infinite measure. And let's see, we would like the empty set to have measure 0. So the set with no elements in it should have size 0. That's fairly obvious. Monotonicity, meaning if A is a subset of B, then the measure of A should be less than or equal to the measure of B. Translation invariance, meaning if I start with a set A and then just shift it right or left by some finite number t, then the measure shouldn't change. Moving my set around should not change its size. Here in property 5, I have countable additivity, but for our proof, we don't even need that, and maybe it's more intuitive to require finite additivity. So meaning if I have a bunch of disjoint sets, each with its own size or measure, and I add those sizes together, I should get the size of the union. Okay, so there's no weird combination effect of these sets, right? If these sets have have empty intersection, when I add all their sizes together, it's very straightforward. I get the total size of that union. And then we would like, since we're trying to extend the notion of length to more abstract sets, okay, if we apply this extension of length to an interval, we should just get our intuitive notion of length of an interval. So this measure we're trying to construct, when I apply it to an interval, I should just get the length of the interval. Okay, so these are the properties we want to show our measure has, and we want to try and show it exists on the power set. And we're going to show that that there's no function that exists with all of these properties. Okay, so we cannot extend this notion of measure to the power set. So this proof requires the axiom of choice, and as you might have guessed from the fact that I found it in a book dedicated to the axiom of choice. It begins with the axiom of choice after a slide or two. So we're going to start by defining an equivalence relation on the set, the interval 0 to 1. Okay, so this relation, x will be related to y if and only if x minus y is a rational number. And I'll let you guys check on your own. This ends up being an equivalence relation. And so, as with any equivalence relation, this divides our interval 0 to 1 into equivalence classes. So, disjoint equivalence classes. Well, all equivalence classes are disjoint, I suppose. But the key here is that it's going to partition our interval 0 to 1. And now here's where our axiom of choice comes in. So by the axiom of choice, we can choose one element from each of these equivalence classes and group them into a set M. And so stating that rigorously, we can say M is the range of our choice function. Now, we can use this M to partition our entire real line. So let X be some arbitrary element of the real line, some arbitrary real number. It should be fairly obvious that there exists at least one rational number R1 such that X minus R1 is in our interval 0 to 1. Okay. And then I have an element in Z in 0 to 1. So there, Z is in some equivalence class in 0 to 1. So there exists some R2 in the rational numbers such that Z minus R2 is in M. And then if I let R equal R1 plus R2, then X minus R equals Y in M. So I can, let's say for any number X in the real line, on the real line, I can subtract some rational number and get an element of M. So I can say X equals Y plus R for Y in M and R in the rational numbers. And it turns out that this decomposition of X is unique. And we can show that by assuming that there's two such decompositions. So assume X is equal to Y1 plus R and is also equal to Y2 plus S. Then Y1 minus Y2 equals S minus R. Since both S and R are the rational numbers, we have Y1 minus Y2 is a rational number. So by our definition of M, we see that Y1 and, by the definition of our equivalence relation, we see that these two are related. Okay, so they're in the same equivalence class. Meaning, if they're both in M, remember I'm choosing a unique element from each equivalence class, they're both in M, that means Y1 has to equal Y2. And since Y is unique, we immediately get that R is unique, right? If X minus R equals Y, so then R has to be uniquely determined. We can't have two different values for R. All right, so now we can use this this decomposition to partition the real line into disjoint subsets. So fix an R in the rational numbers and define MR as this, Y plus R for all the Y in M, okay? And then note that our real line equals the countable union of these MRs, okay? So it should equal the union of MR, and then that union is countable because the rational numbers are countable. So we have the real line is partitioned into these countable subsets MR. So you might be wondering why this is a partition of the real line. Well, for any X in R, we've shown that X equals Y plus R. Okay, so X is in some MR, right? And we can show that it has to be in a unique MR because let's see, if X is in two of these different sets, then we can show, let's see, let's assume we had y1 plus r1 and y2 plus r2. Again, do that same subtraction trick we showed in the previous slide to show that these y's are unique. So if we can try and show that x is in two different MRs, but we'll see that they actually have to be the same MR. Okay, so now we have this set M and we have this countable union M of MRs that partitions R. So what? We're going to try and show that M is non-measurable. And to do that, we're going to actually assume the opposite. We're going to assume it's measurable and then find a contradiction. Okay, so the first step is pretty straightforward. So we're going to divide it into cases. So case one would be assume the measure of M is 0. Now, note that each MR is just a translation of M, right? So MR equals Y plus R for all the Y in M. So MR is just a translation of M. So if this measure has the properties we want, the measure of each MR should be equal to the measure of M. Okay. And we said that the measure, excuse me, the real line is this partition of MRs. So we have R equals the union of MRs. So the measure of R should be equal to the measure of the union of the MRs, right? And then let's see, since these are all disjoint, we actually are going to use countable additivity here. So we do need a bit more than finite additivity. But again, that's not too much to suppose. You know, that is a property we would like. So the union of the MRs, okay, should have the same measure as the sum of the measures of the MRs. Okay, and since each one of these has the same measure as M, which we're supposing is 0, we see that the measure of the union is going to be 0. In other words, the measure of the real line is 0. So if we assume M is measurable and has measure 0, then we get the measure of the real line. The entire real line is 0, which is obviously a contradiction. Okay, so we see case one is impossible. We get a contradiction. So if M is measurable and the measure is 0, we get a contradiction. Now, what's the other possibility? Assume M is measurable again and has positive measure, has measure C greater than 0. Then we consider the union of the MRs where R is in the set A, which I define to be the intersection of the rational numbers and our interval 0, 1. Okay, so R is some rational number between 0 and 1. Now, we can again derive a contradiction. Okay, so if the measure of M is some positive number, then we can see, okay, if I have a countable number of those and I add them together, I'm obviously going to get infinity. Okay, so I have infinity equals the sum of these measures. Okay, and again, since these are all disjoint, the sum of the measures should be the measure of the union. Okay, and then if I pick any point in this union, the point should be in the set 0 to 2, right? Let's see, what is MR? It's defined as the y's in my set M plus some R in our set A. So some R between 0 and 1. So let's say, for instance, what's the largest number that Y could be? 1. Okay, and what's the largest number R could be? 1. So our element in MR, the union of the MRs has to be less than or equal to 2, and by the same token, it's got to be greater than or equal to 0. So we see that the measure of the union of MRs has to be less than or equal to the measure of our interval from 0 to 2 by monotonicity, right? This union is a subset of my interval 0, 2. So the measure of my union has to be less than or equal to the measure of my interval. In the book, the the Axiom of Choice by Jack, he actually uses the interval 0 to 1, and I looked at that for quite a while and couldn't understand how he got the finer subset 0 to 1. So I eventually just came to the conclusion that, well, we could use 0 to 2 and it wouldn't change anything. But if any of you understand how he got 0 to 1, please let me know. Okay, so what do we conclude? We have, okay, the measure of the interval 0 to 2 is greater than or equal to, it has greater than or equal to the measure of this union, which has infinite measure. So that implies that the measure of my interval, my finite interval, is infinity. So my finite interval has infinite measure. Again, a contradiction. So since these cases, cover all possibilities for measure of M, we see that M just can't have any kind of well-defined measure. So M has to be non-measurable. So M is non-measurable. So remember what we were trying to show. We were trying to show that we could extend the notion of measure to all subsets of the real line, okay? And we derived a contradiction. So the contradiction just comes from the fact that we can develop this extension of measure, but we can't apply it to all subsets of the real line. So we have to choose the sets we deem measurable and those which we do deem non-measurable. So how do we deal with this? Well, this is where the development of measure theory comes in. What we'll end up doing is considering this, we'll divide up this power set into non-measurable and measurable sets, and we're going to group all these measurable sets together into an object that has nice union and intersection properties and complement properties, things like that. And the name of that, and what we will need for the development of measure theory, is the sigma algebra. So sigma algebra is going to be what we dump all our measurable sets into, and it has really nice properties that allow us to work with it in a fairly intuitive manner. And it's pretty amazing. They are widely used in probability theory and lead to something called a filtration, which is really cool because it ends up representing the flow of information in a probability space. So we have a mathematical way of representing information, which is extremely interesting to me. And they're the basis of measure theory, abstract integration, Lebesgue integration, a lot of the advanced tools we use in mathematics. So that will be where we go next. I hope you enjoyed the video. Again, this proof is from the book, The Axiom of Choice by Thomas Jack. And I believe this proof actually comes from Vitali. So due to him in early 1900s, not long after the development of the Lebesgue integral, I believe. So fairly modern and has seen, widespread use, I would say kind of universal use in mathematics. So really interesting, and hope you enjoyed it.